very clever way to polarize helium-3 so that neutron had a definite direction. Then he had a brilliant insight just talking to his friends. They were complaining about the inability of an MRI machine, magnetic resonance imaging, which is really nuclear magnetic resonance imaging, but they don't use the word nuclear at the hospital. Nuclear magnetic resonance imaging of the lungs. This is what a picture of your lungs looks like in an MRI machine. Has anyone sucked on helium gas from a balloon? Yeah, it's inert on that periodic table. It's on the inert side. What if you sucked in a little Gordon's polarized helium-3 gas and did the MRI? That's this picture. So Gordon came up with an idea. He's working with his friends. He was actually Princeton at the time, listening to people complain about their inability to do MRI of lungs. Says, hey, I have polarized helium-3. Let's try it out. They literally tried it in a baggie and a straw, sucked some in, did the image, and pow, it worked. So Gordon cares. Who else cares? Tom Crady-Bono. This is one of my colleagues from when I was doing my PhD. He went to work for Schlumberger. Oil exploration. What the heck does oil exploration have to do with nuclear physics? How do you know where to drill? Schlumberger is a company, been around almost 100 years now. They tell people where to drill. What Schlumberger does, they drill exploratory holes. They then put a particle detector and a radioactive source down the hole, taking data the whole way down. They can tell you from the data exactly what the rock formations are all the way down the hole. So they're using particle detector techniques to map out, down over a mile, all the different rock formations. And when you're drilling for oil, you look for certain formations to know where to drill. So oil exploration also relies on nuclear physics. Thea Keppel cares. She works here at Jefferson Lab and was scientific director at the Proton Therapy Center here in Hampton. Inoperable tumors. How do we go after it? We have built here in Hampton Roads a proton accelerator, leveraging the resources and knowledge of people here at Jefferson Lab, as well as some very charismatic people at Hampton University, all got together. They built a proton accelerator here. And what's really cool about protons is they stop very suddenly. So if you have an inoperable brain tumor, I can put a beam of protons through your skull, through your brain, and have them stop on the tumor, leaving all the radiation right on the tumor. Thea cares. And this is just a huge windfall for Hampton Roads, world-class center. And finally, who else cares? And this is probably the oddest example of all. James Simmons cares. Last I checked, he was the 88th richest person in the world. James Simmons was the originator of quantitative finance. He took the techniques and skills, mathematics, etc., that we use here in our everyday research and applied it to finance. His original paper dates back from the late 60s. So his company is one of the first. What's amusing about his company, he will not hire you with an MBA. He doesn't want business majors. He only hires PhDs in math and science. He can teach anyone business, but he can't teach many people quantum mechanics or differential equations, Monte Carlo simulations, all the tools that we use and scientists just know a priori. He hires some of our best and brightest. They apply that to business. And I think that number speaks for itself. He's done extremely well at quantitative finance. So there's just a few examples. I tried to span the gambit of things beyond basic research that have come from Jefferson Lab. So, time to wake up and ask some questions. Thank you. Yeah, back.
What's the purpose of sending the electrons around the track 5 times?
Excellent question. So the reason we're sending the electrons around the track 5 times is each time around they get more energy. So at a facility that came before us in California called SLAC, they took the electrons and they accelerated them down a mile through accelerator. And it turns out it's the accelerator pieces that are extremely expensive. So the clever idea they had for this facility is let's bend the beam back around, and magnets to bend the beam around are cheap. So we accelerate, bend around, and I go right back through that same accelerator again to get even more energy. And it's all about money. I can put the accelerator in a smaller footprint, and it's just cheaper to build, and I get to the same energies. Yep.
Okay, go back to that. Why is it limited to this 5 times?
What will limit you in the end, and actually we have basically hit the limit with our 12 GeV upgrade, as a charged particle gets bent around, it'll start emitting radiation, single charge radiation, and that grows very fast with energies. So eventually you'll hit, the radius is basically too tight. So it's almost like a race car at the racetrack. If we get to 200 miles per hour, 30 miles per hour, I just can't make the turn. So same idea, different situation. Yeah?
How long is exactly like roughly 1.5 miles?
Roughly a mile. If you start from the injector, go around and go into the hall. Yep. So in the hall, some of the domes are bigger than the others. So I always talk tonight about one of our experimental halls. They had 2 spectrometers. What I didn't mention is those 2 giant spectrometers can move. We can rotate them at an angle. So we need a huge room to be able to do that. And we have, that particular hall has the biggest dome. The hall immediately beside it has a very small dome. Their detector basically looked like a giant hollowed out egg. Nothing moved. So an enormous detector, but it fit in a smaller room because they didn't need to move anything. So those hills are really custom, or built above customized setups for each of the experimental halls. And the idea was different experiments needed different setups. In a very general level, Hall A was 2 microscopes that could move. Hall B had a static setup. In Hall C, we could build whatever you wanted.
You mentioned that when you're talking about funding, most of the funding, all basically named were federal agencies. Is there any private people that invest in this kind of research, any private corporations?
So one of the biggest at the moment actually is the Simmons Foundation. So Gene Simmons, who was originally a math professor, then went into quantitative finance, has helped directly with the funding of our sister lab at Brookhaven. But probably the more important thing he's done is created the Simmons Foundation, which is providing a lot of money for something called the Archive, where we as scientists put our work so it's publicly accessible. So yes, there are some private revenue streams. For our federal funding, I think what's most important is our international collaborations and the international money money that comes here. Because it's really easy to raise your hand and say, I want money. It has a lot more weight if you also get the colleagues from Japan or Germany or anywhere around the world that also say, we want to do this and we're willing to contribute. That helps tremendously. In a lot of our big experiments, we built big international groups where they all bring in their manpower, their equipment, their money, come here to help get it done. Yeah. Go.
With an electron turret with energy, correct?
Yes.
So why don't you just make it, like, just unfold it from, like, an oval is just a straight line, so it doesn't lose any energy, it keeps accelerating and accelerating and it hits the speed of light.
So the question was, why not just make it a straight line?
Yeah.
And you also mentioned speed of light, so I'll hit both. So our friends in California at SLAC did the straight line accelerator. It's more expensive. It's as simple as that. It's more expensive to make a long, straight accelerator than to make the oval setup. But you're right, they can get to a higher energy. They'll never have the limitation of the bend. So trade-off. The particles we accelerate here at Jefferson Lab, we take an electron, the smallest fundamental particles we know, and accelerate it as hard as we can. 12 billion electron volts. It's going 0.99999, the speed of light. Brute force, you can't get past the speed of light. We keep putting in more energy, it's still going the same speed. You never get exactly to the speed of light. Yeah.
Always have to go through the writing so that we can see what happens. And you always have to teach us. I want the part. Me and my mate, you always say the same place, the same out, the same rating.
So it's very much so when we're doing an experiment here, it's very statistical. So I'm taking a foil of carbon, I'm putting the electron beam on it, and I'm looking at lots and lots of events so I can figure out what happens. So it's almost like playing a game of pool where someone's always setting the balls in the same place, and you're firing the cue ball in there, and you see where the balls come out, but you don't actually see the moment that it hits. I don't see that part, and that's actually makes nuclear physics really hard. I see what comes out. I have to figure out what happened. But you do enough experiments, if you watch the pool table, even if you never saw that rack of balls, you could figure out it was there by seeing where all the balls go when you fire in from different angles. Yep.
Is this alien that's underground?
Yes. So when Jefferson Lab is running, we have something called prompt radiation. It means there's radiation when our machine is on. There's radiation from the electrons bending. There's radiation from the electrons hitting a material. We turn our beam off, almost all the radiation is gone. With the exceptions of the material I'm hitting where it's passed the beam through, it will still be activated and our dumps. So if you look carefully from Jefferson Avenue, you'll see little tails behind those domes. They have large vats of water at the end that catch the beam. We aren't in there when the beam is running. You know, and they're very careful to make sure no one's in there when the beam is running. So beam running, everyone's out. We have a key system to make sure no one is in. Yes. Yeah. So it'd be electromagnetic. So alphas and betas would be hitting a target material and knocking stuff out. Here in the back?
As I understand it, as something goes to the speed of light, it also increases in size. Starting off at this, by the time you get to 12 volts, or 12, whatever the number is, and how much larger is it than this?
I don't think large is the right way to look at it, but you can look at it as massive. Mass. So an electron in the units that we're using is half a mega electron volt. You can say half an MeV, and we're accelerating it to 12 GeV. So we put more energy in it than it weighs, which is an unbelievable amount. I mean, we've seen pictures of a nuclear explosion. We took some material and turned that material partially into energy. We take the electrons here. We've now put more energy into them than their mass. They're still not going faster than the speed of light. Now, whether you want to look at it as it gained mass or it gained energy, it's two sides of the same coin. And quite frankly, it really depends on how you want to look at the information you're getting. Whether you want to think of it as a very massive thing coming in or a very energetic thing, it doesn't matter. E equals mc squared. Energy, mass, there's an equivalence there, so it's okay. Yeah.
When you run the machine, it's emits radiation. So where does this radiation go when you're not using it?
So the question is, where does the radiation go when we're not using it anymore? So, for example, I said we turn the electron beam, it's making radiation, I turn it off, it's gone. So electrons going around the arc are emitting a lot of photons. They're being absorbed in the walls down in the hall. And as soon as you turn it off, all those photons are going into the light, bounce around, hit the walls, get absorbed, they're gone. It's going into heat. The same thing is going on when you go through the X-ray machine, or your bag goes through the X-ray machine at the airport. They're putting radiation on your bag. They're looking at what passes through the X-rays, passing through the bag, and what's getting absorbed. Turn off the machine, it's off. Or your microwave oven. Microwave ovens.
What's the carbon part?
It's just a foil. I ordered it from a company called Goodfellows. They will send you a nice big sheet of carbon. We cut it down to a nice foil, put that foil in the beam so it's perpendicular, run the beam straight through it. It's a very simple setup, and it's very easy to get homogeneous carbon, pure carbon. But the wall's made out of concrete. The wall's made out of concrete. Protons are getting rid of the tumors. So again, the idea is that radiation can damage cells. Right? That's kind of why we worry about getting exposed to radiation. It can damage cells, you can get a tumor. On the other hand, if I can put the radiation in a controlled way, so the proton therapy machine here in Hampton, very carefully, they would do an MRI. If you had a brain tumor that was inoperable, means I can't operate to get it out. I'd do an MRI scan of your head. I'd locate exactly where the tumor is. And then I would put the protons exactly on the tumor. The technology to build a machine like the proton therapy machine has been around for decades. The problem was we didn't have the technology to make use of it. You really need an MRI machine. I need to be able to scan the brain to where the tumor is very precisely. I don't want to put the proton beam and have the proton stopping on good tissue. I only want to know the bad. So I need an MRI and I needed a computer. I needed a powerful computer really to control where I'm putting those protons. So it's really a clever trick. I'm going to put protons. I don't have them stop just on the tumor, just on the thing I want to kill. Because I can use radiation to kill the bad stuff too. So in this case, we're using radiation to do something good. Yep. Let's speak up. Oh, okay. Yep. if you had the proton machine in there, hitting you with protons, radiation get in your body? A little bit, and there are trade-offs. So most of the energy from the proton will stop on the tumor, a little bit goes through your brain, and a little bit will get absorbed. The clever thing that they do when you go in for a brain tumor treatment, you come in one day, they send the beam in from your left side, next time from the right, and they come in at different angles, so they're not going through, so go through different parts of your brain, give very small doses possible to brain tissue, good tissue, while maximizing the dose on the tumor, try to kill the tumor. Any small amount of radiation can harm you, so you want to keep it minimal, but very small amounts have been shown to do very little. In fact, we're getting it right now. You're always getting radiation. So the rate of radiation we get right now is called a millirem. We get roughly 365 millirem a year of radiation. And that's just part of being here on this planet. Radiation comes from our sun, hits our atmosphere, cascades down, and there are particles passing through us as we speak. So a square meter, so this table is 100 particles per second are going through this table right now. I can't see them, but they're there. So radiation is around us all the time. And that's one misconception people have about radiation. They just hear radiation and go bad without really learning about it, what it is that is around us. And there's a trade-off between medical applications of radiation. When you're at the dentist, you get a dental x-ray, look at your teeth. So you're getting a little bit of radiation, and the benefits of being able to see the cavities before they develop into something worse outweighs the risk of getting cancer from that little bit of radiation. So it's always a trade-off.
If we could just take a moment, some of you may be getting ready to leave. Some of you may wish to stick around a little bit longer. I'll go ahead and open the door, or you can use the back door. If you need a piece of paper signed for school, we do have staff out front to take care of that. The rest of you are welcome to stay and continue after you've done some.
So if you have any more questions, just come on down. Thank you very much.
I'd like to welcome you all here to Jefferson Lab. My name is Joyce Miller, and I'm a mechanical designer here at the lab, and I'm also the captain of the Jefferson Lab Dog Training Club. So if you were wondering how we got this important person from upstate New York to come to Hampton Roads, Virginia, I also have rescue greyhounds, and I follow a blog written by a fellow greyhound rescuer, and he wrote a little blog post about Mr. Orzel here, and he wrote this blog post about teaching dogs physics, and I thought, well, wouldn't that be a great thing to have here at Jefferson Lab? So I contacted our science education department, and they invited Mr. Orzel to come and speak to us tonight. He is a physics professor at Union College in New York, in upstate New York, where it's cold, much colder than here. And
very, very mild.
and he writes a blog, his own blog, and he also writes for Ford.
Use this to get through the fence to the yard next door. Right. This is another obvious thing that dogs would be after, and this is another phenomenon that's very real. It's called tunneling. Right. And this is a phenomenon where sometimes quantum particles end up in places they shouldn't be able to get to. Right. So how does this happen? Well, again, let's think about an ordinary classical particle. Go back to thinking about a football. Right. You send a football up in the air, it goes up, it slows down, it turns around, it comes back down, and falls, hits the ground, and bounces a couple of times. Right. Now this is a characteristic motion that everybody's seen before. Right. If we want to think about this in terms that we can compare to quantum physics, we need to talk about this as something we can turn into a wave. We need to talk in terms of the probability of finding this football at a given position at a given time. Right. Well, we can do that by sort of turning this thing on its side. Right. So we can make a graph of the probability of finding the football at a given height. Right. And what you see if you do this classically is something that looks like this. Right. It goes up and then comes crashing down. Right. There's zero probability of finding the football below the ground. Okay, that's kind of obvious. And there's a maximum height that the ball reaches, and there's zero probability of finding the ball above that maximum height. Right. The probability of finding it somewhere in between, well, it goes up as you go toward the top, because up here the ball is moving very slowly. It stops for an instant at the top and then turns around. So there's a good probability of finding it there. In the middle, the ball is moving pretty fast as it goes on its way up and on its way down, so it doesn't spend very much time in the middle, so the probability is much lower there. Right, so that's the probability of finding a football at a particular height. Right. Now, if we imagine doing this with a quantum football, things are kind of similar. Right, that's the blue curve here. Right, this looks a little scarier because it's doing some wavy stuff, right? But it has to do wavy stuff because everything in the universe behaves like a wave. Right, but the general pattern is the same. Right, we've got wavy stuff, and the waves get bigger and bigger as you go toward the top, right? Just because the probability increases up there. Right, but the really interesting thing about this is this bit right here. Right, there's a bit above the maximum height where the probability doesn't come down to zero immediately, but tails off slowly. There's some reasonable probability of finding the ball in this red shaded region, which is higher than it ought to be able to get to, according to classical physics. And this is because the ball behaves like a wave. Right, waves don't just immediately, instantly stop. Right, if you go to the beach and look at waves on the shore, they sort of ride up the shore. Right, the waves have to spread out over some distance. There's some extent over which the wave can be found in places it shouldn't be able to reach. Right? And this is what drives the phenomenon of tunneling in quantum mechanics. Right? Particles can penetrate through barriers that they shouldn't be able to get through. Right? Now, that's a weird thing to say, right? We don't see that happening, right? If I run at that wall, I'm not going to end up in the hall outside unless I physically go through the wall, and I don't have enough energy to do that. Right? But we know that this phenomenon is real, and I can prove it to you because the sun shines. Right? It was sort of nice for a little while today. Right? You could see the sun. Right? And the fact that the sun shines is proof of tunneling. Right? How does that work? Well, what's the sun doing? The sun is turning hydrogen into helium and releasing energy. Right? How do you do that? Well, hydrogen is basically a proton. If you take two protons, you bring them close enough together, you can get them to stick together. One of them turns into a neutron in the process. It's nuclear physics, don't worry about it. Right? You take a couple of these guys, you can stick those two together, and you can form a helium nucleus that has two protons in it. Each step in this process releases a little bit of energy. This goes on a lot in the core of the sun, and that energy that's released heats the sun and turns into the heat and light that we receive from the sun. Allows all of us to exist. Right? Now, this is something we can easily calculate what it takes to do this. Right? Because if you're trying to bring two protons together, they're both positively charged, they repel each other. Right? They're going to try and push each other apart. They don't want to be really close together, but you can get them really close together if you throw them at each other really hard. Right? And you can calculate how fast you have to throw them at each other to get them to stick. And it turns out that corresponds to a temperature of 15 billion degrees. Right? And we know what the temperature of the core of the sun is. The temperature of the core of the sun is 10 million degrees. Right? Those are not the same number, right, by a factor of 1,500. Right? The sun is 1,500 times too cold for fusion to occur, according to this simple calculation. Right? So how does the sun shine? Well, most of the time when protons in the sun come toward each other, they just separate. They repel each other and they go back apart. But every now and then, quantum mechanics allows these things as they come close together to just tunnel through that barrier and end up sticking together and releasing the energy that powers the sun. Right? This happens extremely rarely, but there's an immense amount of hydrogen in the sun. This is going on over and over again. Even though this process is extremely unlikely, it happens often enough to allow fusion to proceed and keep the sun shining. Right? So the fact that the sun shines is proof that quantum mechanics allows things to pass through barriers that they shouldn't be able to get through. Right? So does this mean that we're going to see dogs start, quantum passing through fences? No, because the probability of this happening has to do with the wavelength of the particles compared to the size of the barrier, and again, the wavelength of a dog is just too short for that ever to show up. So a follow-up question on this from this reader, so I should just dig a hole under the fence then, and that is also a kind of tunneling, but only bad dogs dig holes. So one more question from a canine reader. I heard that quantum physics says that cats are both alive and dead at the same time. I've always known they were undead zombie monsters. Now my humans will have to believe me. Okay. This is a reference to the video I showed at the beginning of the talk. This refers to a thought experiment called Schrodinger's cat, named after this happy fellow here. This is the Austrian physicist Erwin Schrödinger. He was one of the pioneers of quantum mechanics, but he became disillusioned with the theory for philosophical reasons, and he left physics and left quantum physics and went off and studied other things. But on his way out the door, as it were, he invented this thought experiment to show what he felt was the philosophical absurdity of the theory. Right? And it goes like this. He said, imagine taking a cat, right, and putting that cat in a sealed box. Right? You seal it up good so you can't see or hear what's going on inside the box. And in the box with the cat, you put some device that has a 50% chance of killing the cat in the next hour. And the question he posed is this. At the end of the hour, what is the state of the cat? Now, common sense would seem to say that, well, the cat's either alive or it's dead, right, inside the box. Right? But what Schrödinger noted is the mathematics of quantum physics tell you that the cat is not alive or dead. It's both alive and dead in equal parts, right up until the instant that you open the box and check. Right? And that seems so completely absurd that he rejected the whole theory and decided he wanted nothing more to do with it. Right? If you want sort of a very slightly dated musical rendition of this, right, so here's, hey, I'm Schrödinger, and this is crazy, but here's a sealed box, the cat lives, maybe. So this is a really weird idea. It's also absolutely true. We know that quantum objects exist in more than one state at the same time. Right? How do we know this? Well, because of the experiment I showed you earlier with the single electrons. Right? We shoot single electrons at a barrier with slits cut in it, and each electron acts like a particle. It's detected at a single point at a single instant in time. But if we repeat this experiment many, many times, all of the electrons together trace out this pattern of bright and dark spots that's characteristic of wave behavior. How do you get that pattern with waves? You get that pattern with waves coming from two different sources. That means that during the course of this experiment, each electron behaves like a particle, right, but like a wave at the same time, and it's in two states. It's in the state of having gone through the left-hand slit and having gone through the right-hand slit at the same time. Those pieces come together, and that's what makes this pattern of bright and dark spots. So the double slit experiment done with electrons proves that quantum particles can exist in multiple states at the same time. Now, does that explain zombie cats? Right? Zombie cats might exist, but you can't really blame physics for them for the same reason that you can't see dogs tunneling through fences or demonstrating wave behavior. The wave nature associated with something like a cat is just too small for this to really show up in the everyday world. So while there might be zombie cats out there, it's not our fault in physics. I want to give you one final example of an email that we received after the publication of this book. This one's a little different, but probably very familiar. So it's Dear Dog Physics. I am a retired quantum physicist, and I've discovered an ingenious quantum technique that's worth $100 billion. I will happily give you 50% of this if you will provide me with access to your bank accounts. Right. We all get these kinds of emails. Right? The previous emails were from engaged, interested, nice dogs who read the book. This one's from an evil squirrel, the kind of lurk in the trees outside our house. I used to set my dog off. Unfortunately, unfortunately, there are a lot of evil squirrels out there. There are people who try to use quantum physics in a cynical way to extract money from the gullible. All right, and this takes lots of different forms. There are conferences out there on quantum healing, right, which claims to be able to do medical miracles using the magic of quantum physics. Right, you're simultaneously in a superposition of sick and healthy at the same time, and if you just learn their secret techniques, you can pick the healthy part and then do them. Right, this involves these sort of energy field diagrams that are kind of interesting. There's some new agey stuff that shows up. There's some things that show up that seem designed to cause headaches and nausea that you can then heal with quantum mechanics. Free energy is another angle that a lot of people take. Using this miracle quantum product, you can produce electricity from nothing, never pay an electric bill again.